everyone. Welcome to the another session of digital signal processing. Today we are going to discuss another mathematical technique which is used in digital signal processing to have various benefits, and one of the benefits is reducing the cost of the DSP processor, that is multi-rate digital signal processing. So in this session we are going to discuss the introduction to this multi-rate digital signal processing, what is this, and various techniques to implement this. Out of two techniques that we generally use, they are decimation and interpolation. Today we'll be discussing about the technique that is called as decimation. So what is basically this multi-rate signal processing? As we have been discussing in the previous lecture, different mathematical computational techniques we are implementing for digital signal processing. The very first step that we must know in digital signal processing is about sampling, that any kind of analog signal that I want to process with the help of a digital processor, I need to convert it into digital format. So till now, whatever sampling we were talking about, that was called as a single rate system, because when we talk about a sampling frequency, we generally talk about a basic frequency of, say, I'm sampling my signal as 56 kilohertz. I may sample it at 128 kilohertz and even higher frequencies like 512, 1024 as per the requirement of the application. So I'm sampling the signal at one specific rate, and that one specific rate can be any available specific rate. But what do I see that practically many of the applications require signal which is having a different sampling rate. That means one signal which I have with me that may be generated at sampling rate of 56 kilohertz. The same signal is also required at a sampling rate of 120 kilohertz. So one thing is that I should generate this signal independently at these frequencies twice, and that is not an intelligent decision. That if I'm recording, say, any kind of audio signal, I'm recording any kind of audio or video signal, if I've recorded it once at, say, one particular frequency f1, and now I want this particular signal at different frequencies, say 128 kilohertz, then I would be creating the content again. No. So we have certain mathematical techniques which are called here as multi-rate signal processing, by which this xn can be converted into a signal of different sampling frequency. So in many practical applications, as we talk about digital audio and video, along with this in radios, teletype, facsimile and many other applications, I would require different sampling rate for various signals corresponding to their bandwidth. So in this case, we'll be applying this special technique which is called as multiple rates of sampling, having more than one sampling rate as per the requirement of the application. One of the examples that we can discuss where do we require these different sampling rate, like in the case of digital audio, I would require a music piece at a frequency of 32 kilohertz for broadcasting. The same piece of music has also to be generated at 44.1 kilohertz if I want to store them into my CDs for a later recording. It is also required at 48 kilohertz to be stored in the form of the audio tape. So I have to use a technique in which I can generate that piece of music at these three different frequencies. Similarly, talking about the digital video, different sampling rate would be required depending upon the different TV system we have in a country. So the most popular TV system that we have are NTSC and PAL, and both the system have different specification for the video signal that we are transmitting. So what do we see here? In the case of the system, video signals required are 14.31 megahertz and 17.13 megahertz, but the sampling rate for the digital component of the video signal 13.5 megahertz and 6.75 megahertz for the luminance and the color different signal. So same piece of the video would be required at different sampling frequency depending upon a country which is following the NTSC system of TV or it is using the PAL system of TV. So if I am creating a piece of music, if I am creating a piece of movie, I would have to require this multi-rate signal processing to generate the same piece of music or video to be represented on a different system, maybe playing onto an amplifier, maybe playing onto some kind of system. But the most common reason is that multi-rate DSP can greatly increase the processing efficiency, that is even by the order of magnitude. We'll see that how the efficiency is also being increased. So it reduces the DSP system cost as well. So one is the requirement. I require a signal at different sampling frequency depending upon the application. And the second requirement is that I can reduce the cost of the system by which I'm going to produce or process this particular signal. So here this demand for this multi-rate signal processing is vital for all the professionals which are using this DSP kind of things to process a signal. So both the advantages we look at one after another, that a different sampling rate can be achieved using three techniques: upsampling, downsampling and resampling. The basic operations that we are going to perform here are basically decimation and interpolation. Decimation is basically for reducing the sampling rate and interpolation is basically for increasing the sampling rate. And when we talk about this resampling, it is a combination of interpolation and decimation both. Or we can say when we talk about certain integer values, say I need to decrease the rate by a factor of 4, I need to increase the rate by a factor of say 3, but I tell you that I need to change the rate by a factor of 3 by 4. So when I want to reduce the rate by some factor, I would apply a decimator. When I want to increase the rate by a certain factor, I would apply this process called interpolation. But if I want to change the sampling rate by some fractional order, I would call that process as a process of resampling. So resampling is made up of two basic operations, interpolation and decimation. So in summary, whenever we talk about this multi-rate signal processing, we are talking about two basic techniques which are decimation and interpolation. And we have to keep in mind the sampling frequency we are increasing or we are decreasing. It should be free from any kind of undesirable effects, any kind of errors or any kind of aliasing which may appear because of the quantization process which is felt in the DSP processor. So one by one we'll see that what kind of errors can occur during decimation and interpolation and what are the basic techniques by which we can reduce those errors. Secondly, while designing a multi-rate system, the effect of aliasing for decimation and the pseudo images for the interpolation should be avoided. So as we were talking about, there would be certain errors which would be occurring because of these processing, decimation and interpolation. So when we talk about decimation, I'm going to suffer from aliasing, and when I talk about the interpolation, I suffer from pseudo images which appear into the output signal. So we'll take into the account these two limitations of these two techniques while we are processing our signal using decimation or interpolation. So in summary, the advantage of multi-rate signal processing is that first of all, it is reducing my computational requirement. Also, storage for the filter coefficient, the finite arithmetical effects can be removed. Filter order required in the multi-rate application and sensitivity to the filter coefficient length. These are different advantages that I can achieve with this multi-rate signal processing. So basic concept that we are going to apply both in the case of decimation and interpolation is sampling rate conversion is a process in which I need to convert a sequence xn which is already obtained from sampling the continuous time signal xt. So in a normal process of sampling, what do? I convert this continuous time variable into discrete variable n. This is a time domain sampling. When I talk about this multi-rate processing of a signal, this is same as we're talking about time domain sampling, but the input signal is already sampled. I'll be beginning with this sampled version of this continuous time signal. Either I'll decimate this signal or I'll interpolate this signal. So what I'm doing, initially my signal xt was being denoted with the help of this period t, another sequence being generated which is say yk, and period for that particular sequence would be t dash. So what I'm doing, a t is being converted to some sampling time period t, another t is being converted say at time period t dash. So only time variable which has already been discretized by performing this continuous time sampling, their time period or their frequency is being changed. So the new sequence is being entitled as yk. It can be obtained by first reconstructing the original signal xt from the sequence xn, and then I would sample it again to have a period that is called as t dash. So here I can see this is my xn, discrete signal or a sequence of number that I need to process. I would reconstruct it. Reconstruction is basically the given xn is now being converted to xt. So that is what I'm doing. I'm performing inverse process of sampling. So what I have to do? I have to do D2a conversion. This is discrete signal. From this discrete signal, I have to calculate this continuous signal. So this is D2a conversion. So that's why in this block diagram, the first thing is I'm performing this D2a conversion and I'm getting this xt. Now I would have to resample this at a different frequency. Frequency and time are reciprocal to each other. So what I can say, I can talk about frequency, I can talk about time. Both are being changed in the process of sampling rate conversion. This x would be passed from low pass filter so that as aliasing effect that is generally encountered in sampling process is removed. And then here I am using a switch. And the sampling frequency of this switch is depending upon t dash. So initially this xt was sampled at say time period t. Now it is resampled at a new time period t dash. Now k can be any kind of integer value. Here for simplicity we can take this k as 1, but it can be any step size 2, 3, 4 as per the requirement. So only two steps are required. First, converting a digital signal to analog signal, and this obtained analog signal would again be sampled at a different frequency or at a different sampling time period. So this is how we're converting the rate of the sampling. Now talking specifically about two phenomena. One is decimation and interpolation. I need to change the sampling rate. Now this change can be in the form of increase or in the form of decrease. So when I need to make this process, here this entire process is decreasing the frequency or increasing the time period between two samples. This process would be carried out with the help of interpolator that we are going to discuss in next session. But when we are going to decrease this rate, the output signal has less frequency, less number of frequency sample as compared to the input sample. This is being achieved with the help of the process called as decimator. So the process of reducing the sampling rate of a signal without resulting in aliasing. Now this is important. I need to process a signal so that any kind of error should not appear at the output. So I would reduce the sampling rate and I would also try to remove this effect which is called as aliasing. This is called as sampling rate reduction or decimation. So let me assume that I want to reduce the sampling rate by a factor m, capital M, and this m is integer. So what I have to do, I have to reduce this by a factor m and the signal given is xn. So this is my signal xn which is currently having a frequency f. It is passed through the filter hn and I am getting an intermediate signal Wn with the same frequency, because this filter is not going to change the frequency of the signal. Now this filter is required because I want to avoid this process or this effect which is called as aliasing. If I do not place this filter here, then whatever I am getting at the output would be the aliased version of the input. That means the high frequency would be overlapping with the lower frequency and the envelope or the output that I am receiving would be distorted. So this is my low pass filter, and this low pass filter is also called as anti-aliasing filter. So this is a necessary requirement whenever I am implementing this process of decimation. Now this is basically, this area is something which is showing me up reducing of the sampling frequency by a factor of m. So after this process, see that there is a change in the frequency f dash, which is equal to 1 by n times of fm. I am scaling the given frequency by a value m. This is same m which I am using here for carrying out the decimation by a factor of m. So this n can be any integer number, 2, 3, 4 and so on, and it has to be integer. Then only I'll be calling this as a process which is directly reducing the number of samples. Talking about in the terms of time, t dash, the new time which I am obtaining, sampling time, divided by the old time, this ratio is equal to m, or I can say the new time is m times the old sampling time. So both of these things are representing the same expression, one in the terms of frequency, another in the terms of time. So what is going to happen? If I am going to plot certain kind of sample signal, these signals would be far away. The distance between these signals would increase, showing the sampling time has increased or the frequency has decreased. So what this particular block diagram is doing, stage by stage, I take any signal and its Fourier transform to see the spectra of that input signal, that is corresponding to this xn. Two things are being done. One is the filter. What should be the quality of this particular filter? The response should look like this, h of omega. The gain of this filter should be 1, for which range of frequencies? Omega should lie between minus pi by m to pi by m. Then only my decimation process would be free from aliasing. This m is representing the same integer number m by which I am reducing the frequency. So if this particular filter which I have represented here is having this particular characteristic, that it is allowing all those values of the signal which lie within this range of frequency, the output would be without the effect of aliasing. Whenever I am using this filter, this output Wn is represented as convolution of these two, the system transfer function and input transfer function. The same thing has been read here, that this Wn is the convolution of given signal and the transfer function. Once I am getting this particular signal, I am decimating the frequency by m. So here Ym is equal to W capital M into M. So here I can replace the value of n with capital M into M to get my final expression for Ym. So these are two formats of the convolution theorem, that either I can take hk constant, delay xn, or xn constant and delay my transfer function, representing the same thing. So this signal which I am getting, W dash n, this is Wn only, but available only at certain values, that is 0th, mth value, twice of mth value and so on. So I am losing certain amount of samples in a given signal. So this is a frequency spectrum by which I can read out the entire process which is being followed for the decimation. This is the spectrum for the input signal xn. This is the spectrum or response for the given filter Hn. Because this is the frequency representation, I would simply multiply these two signals, because convolution in time domain is equal to multiplication in frequency domain. I would multiply these two signals and I would have this spectrum corresponding to my signal Wn. And this is Wn, which is going to be decimated by the factor m. So this is the output corresponding to my system, for which we have just shown the block diagram. So I can see that these two are same. What I see, these are the replicas of these particular signal that I am obtaining. So what I can see, that out of all the values of the sampled signal, I would be having few number of the sample values, but the shape of the signal which I am giving to the input signal, that should not be distorted. So this is how we see the same spectrum in the digital domain by the Z transform as well. The same flow of diagram which we have done here can be represented by the Z transform as well. So we can show the entire spectrum evaluated onto the unit circle by this particular spectrum, where H is my low pass filter and X is my input signal. And so on, I can represent it in a more precise expression, that how my Y is going to be appeared, that decimated output is going to be appeared. What do I see here? That these are two spikes of my signal available at 0th and 2 pi frequency, which I give it to my signal. This is something which I am obtaining different samples at different values. That means there is a slight difference between all the spectrum which I am obtaining. There is no overlapping. This is what we were designing, a spectrum without aliasing. So if I am using a low pass filter which is band limited to this particular range, this kind of output can be obtained. But if we fail to save this particular condition, I would see this kind of spectrum is obtained. What do I see here? These are the areas of overlapping, and my spectrum would be like this. So which is not at all similar to this given spectrum. So this is which I call the spectrum with aliasing. So I have to make sure that whatever process I am doing, this kind of overlapping is avoided to get a aliasing free output after the process called decimation. In a normal thing, if I see what is the effect of decimation to a signal which is having certain discrete values. So I need to obtain a decimated signal Ym for this given signal Xn, and I need to decimate by a factor of 3. That means the capital N given here is 3. So what I can see here, for this particular block, this same signal is being repeating itself. So let's just apply the decimation to the first section. The same kind of decimation would be proceeded for the another samples as well. Samples are available at first sampling period, second, third, fourth, fifth and sixth. When I talk about m is equal to 3, that means I have to pick up every third sample. That means if I am picking up this 0th sample first, then it will be 0th, first, second and third, first, second and third, and so on. I would keep on picking up every third sample, and all other sample would be lost. This is in a simple way I can represent a decimated signal. So for this given signal that is having the value 0, 1, 2, 3, 4, 5 and 6, I am only having the value 0, 3, 6. This is for the first section. Proceeding to the another section, again I would start picking the third sample. So I am getting second and fifth sample. All the intermediate samples which were available here, they were all lost. But because we have used the anti-aliasing condition alive by choosing the low pass filter Hn to have a spectrum of frequency to fall in a range minus pi by m to plus pi by m, the spectrum which I'll obtain for this ym, corresponding y omega. When you plot that y omega, the same kind of spectrum would be obtained, which would look like the spectrum of the given signal. So even after losing every 2 samples between the given number of samples, my shape of the signal remains the same. So this is how the decimation is implemented without aliasing. Another algorithm that we have to see for the same interpolation process, increasing the number of the sample, we'll be discussing into the next session. That's all for this session. Thank you.